Okay, so we've looked at both Coulomb and Rankine theory, and the last one we're going to look at is the log spiral method, and it's a method we use really only for passive earth pressures. So one of the things we're going to do in this section is, after we go through the log spiral quickly, look at how the three different methods compare, particularly in passive earth pressures. So the log spiral, the log spiral is a very interesting little mathematical formula. It has, the equation for the log spiral is, actually the equation is just that R is equal to R0 times e to the sum b times, time e to the theta times sum b. There's two constants in the log spiral. There's R0 and there's this b. And theta, this is theta. Theta is the angle of the log spiral. There's a lot of interesting things about the log spiral. You can derive the golden rectangle sizes from it and all kinds of things. And you see it a lot in nature. If you cut a nautilus cell in half, it has a log spiral, all kinds of interesting things. What's interesting for us is if we use for B this second constant, the rotation constant, the tangent of the friction angle, then the log spiral has this very interesting property that the angle between the normal and the direction and the center of the point will always be at phi. So at any point along here, the resultant of the frictional force on the surface will act through the center of the log spiral. So what's really convenient about that is if we sum moments about the center of the log spiral, neither the normal forces nor the frictional forces along the spiral have any moment. The only thing that has a moment that is going to be c. And so it's a really simple solution, and it turns out it satisfies equilibrium, but satisfies both force and moment equilibrium. So it's a nice little mathematical thing to do that makes it really easy. And it's been used for many, many, many decades, probably centuries. So that's the log spiral method. Now, and it's used a lot in slope stability analysis. So it's very tractable. It's kind of a hard solution to solve by hand, but it's easy to solve with a computer. And so it's very attractive because it's very quick. So if you and it's probably the fastest solution you can do for a limit equilibrium analysis for a uniform material. It obviously doesn't work if you have layered soils. But I'm not going to go through and derive this or go through the solution method. But I want to talk about a little what log spirals look like. Now, before we assumed, remember that we had a planar surfaces, both in Coulomb, in the Coulomb and in Rankine theory, we have planar failure surfaces on our walls. In this case, I'm using a wall that's moving to the left. So this is going to be the active side, and this is going to be the passive side. And this is generally the way our problems are set up. Our walls have some. They're buried in the ground to some distance, and we have some passive resistance on the face of the wall, and back behind the wall we've got active earth pressure conditions. So we want to be able to compute the passive forces. Now, if this was our critical angle for Coulomb, if this was phi crit, I'm sorry, it's not phi crit, it's theta crit. And I solved a log spiral for it. That's what the log spiral might look like. I don't know if you can see that, but it's curved. But the spirals that we get, they give us the maximum, the earth pressures and stuff, but they're pretty close to planar. They're not tremendously curved. We're not back at the beginning of the log spiral. We're not back in this part of the log spiral here where there's a lot of curvature. And that's just the way that the solutions work out, which they should. I mean, we're getting pretty reasonable solutions with Coulomb, so the log spiral curve shouldn't be too much different. However, on the passive side, I hate it when it does that. I don't even know what it's doing to do that. On the passive side, we can actually get a very, very different log spiral than the surface. In fact, we can actually get log spirals that come in and do stuff like this. So on the passive side, the critical failure surface for a log spiral is very, very different from the planar surface that we get from both Coulomb and Rankine. And we know it's a better solution because what were the equilibrium equations we used in both Coulomb and Rankine? Well, in Rankine, we didn't use the equilibrium equations. We just assumed that the soil was in a general state of failure. In Coulomb, what were the equilibrium equations we used? Just forces, right? So we did some moments. So the Coulomb method does not satisfy complete static equilibrium. We didn't do a summation of moments. We just didn't do it. But the log spiral, you can prove this if you look at the log spiral, it satisfies all equilibrium equations. So it turns out that on the active side, we're not going to get very different solutions from the log spiral and either the Coulomb or the Rankine, but on the passive side, they can be substantially different. So it's important to look at those. Since the log spiral solution is difficult to solve by hand, mostly it's done with charts. I gave you a spreadsheet that does some of it analytically for you, and I'll show you how to use that in just a minute. So the charts are usually laid out in terms of ratio. So on each of these charts here is a ratio of beta over phi. So beta is the back slope angle. So almost all the angles that you use for this are ratios of beta to phi. And so you've got phi here. These are ratios of beta to phi, and then there's I'm not going to go through this whole thing, but there's and here you've got your delta angles on the active side, assuming that delta is equal to phi. And over here you have reduction factors for your k based on the ratio of delta to phi, if you can see that. So if the ratio of delta over to phi is, these are for the passive, so if you got 70% if delta is 70% of p, then you use these reduction factors based on phi. So it's a kind of a tedious little chart solution, but because the numeric solution is not as simple as 1 minus sine phi or just a whole bunch of cosines, you've got way too many terms in there. So this is the most common way that it's done. There's a Carousel and Calco and Carousel put out a book of these in the, I want to say the 70s or 80s, back when numerical computing was hard, and they have this whole book full of chart solutions for this. But this is commonly the way it's done, and I'm pretty sure I provided you this chart. I'll look here in just a minute. I ran some numbers for you. This is one of the additions today, because I've talked about this before, but I never ran the numbers. These are, I'm comparing here, I'm only comparing the passive side, but the active side is not that big a deal. On the passive side, it's a much bigger deal. So I'm comparing Rankine, Coulomb, and the log spiral Ks, and these are only for horizontal ground surfaces and a vertical wall. So this is for, if we go back to this figure, these are for alpha is equal to 90 and beta is equal to 0. And by the way, you need to be careful when you look at these solutions about how they define them. Some people define this as alpha. I'm going to call it alpha star. So when you look up somebody's equations for Coulomb, be really, really careful about how they define the angles, because some people define alpha as the inside angle, some people define it at this angle. Beta is almost always defined this way, but it's alpha that's commonly done differently. So these solutions happen to be just for horizontal ground surface and a vertical wall. So this is for for ours, alpha is equal to 90 degrees and beta is equal to 0. And I did it for 3 different friction angles, 30 degrees, 35 degrees, and 40 degrees, and then these ratios of delta to phi, so 20%, 50%, and 75% of phi. Okay? You understand how the chart's laid out? Everybody good with this? Okay. So if you look at Rankine, obviously there's no change in the Rankine earth pressure as a function of delta, because delta is equal to 0 for there. I mean, there's no delta for that one, so they're the same. So in Coulomb, the only difference the difference between these three values is the angle of delta. So the first thing that tells you is delta is pretty important in the Coulomb solution. I mean, you go from if you're taking delta as half of, I mean, just compare these two numbers in every one. Taking delta as 20% of the friction angle versus 75% of the friction angle changes your earth pressure coefficient, by a factor of 2 to 4. So that right there tells you the big difference between Coulomb and Rankine. In Rankine, you're assuming that the direction of the earth pressure is parallel to the back slope angle. In this case, it's horizontal, and that wall friction angle makes a significant difference in your earth pressure coefficients, especially as the wall friction angle gets large. And then for the log spiral, I'm comparing the values here for the log spiral. Now you'll notice that for low friction, for low internal friction angles and relatively low cohesion, there's pretty good agreement on the passive side between Coulomb and the log spiral. But what happens as the friction angle gets higher between those two? Yeah, which one gets larger? The Coulomb gets larger than the log spiral, right? And which one is the more accurate solution? The log spiral, right? And where does Rankine fit in all these? So log spiral is the theoretically best solution of these, all we've got for passive pressure, right? So these data are pretty important. All right, so when you get to high friction angles and high values of the wall friction, Coulomb gets unconservative, and it can get significantly unconservative. And Rankine is always low and conservative. Now, people don't like using the log spiral because it's kind of a pain in the butt, because it's not as easy as 1 minus sine phi over 1 plus sine phi. You either got to look it up with a pretty obnoxious chart like this, or you've got to run a little computer program, which I'll show you in a minute. So the log spiral is kind of a pain in the butt to do, because you can't just sit there. You can't just sit there with your calculator and in 30 seconds and calculate it. But if you need really good passive earth pressures, it's important. So but you can always use Rankine because it's always going to be conservative. So that's the good news. So if you want a quick calculation, you can always use Rankine. It'll give you a conservative passive earth pressure. Because in general, we don't want a high passive earth pressure. In general, passive pressure is going to be resisting things from walls, and we don't want high ones. If you're in a situation where you got a problem and it's the other way around, where high is conservative and low is non-conservative, I'm trying to think of an example where that might be the case, and I can't think of one offhand, then the story is the other way around. So let's talk about these three methods. So if we're looking at non-failure planar surfaces, which maybe we'll look at the log spiral. On the active side, there's little difference. What's the biggest difference in active earth pressures? It doesn't have to do, but it's not the difference between log spiral and, I didn't show you the active ones. There's a little difference between the failure surface, and the active pressures aren't that much different. In the passive condition, though, there's significant difference in the shape of the failure surface. And the Rankine will almost always underpredict the passive pressure. So if you're using passive resistance, that's always conservative. And Rankine is easy, right? The Coulomb can overpredict, and it can overpredict significantly, particularly when you have large phi and large delta angles. As phi goes up and as delta goes up, the deviation between the Coulomb and the log spiral gets really significant. What's happening there is, as you get large delta and large angles, this slope gets really shallow, where the log spiral comes up shorter than that. And so the Coulomb's giving you a wedge that goes way, way back. And the soil's not going to fail that way. It's going to, if you have a really shallow wedge like this, the soil's not going to fail that way. The failure surface is going to pop up earlier, and that's exactly what the log spiral method gives you. So what's the recommendation? Well, don't ever use Coulomb for passive. That's kind of like the bottom line for this. It's just a bad idea. Because first of all, when we get into design, we'll talk about all the issues. There's a lot of potential problems with depending on passive earth pressure in design. We'll talk about that more when we get there. So using Coulomb for passive is basically just a bad idea. Rankine is always conservative, so you can use it. And if you want the right answer, you should use a log spiral. Whoops. So that's kind of the bottom line for passive. And I won't do it today, but I'm going to add this. Well, I'll talk about that in a second. Never mind. My brain's getting ahead of my mouth, so I'll give it a chance to catch up. Okay, I want to show you. Oh no! Before I show you that, no, I'll show you this first. Let's see. So since log spirals are kind of pain in the butt to calculate, I gave you this. I gave you a copy of this program called PYCAP, and it was developed by Makva, who's one of Duncan's PhD students, and he was looking at how the passive resistance of pile caps. He was looking at the pile caps and lateral resistance of piles. So he was specifically looking at the pile caps, but his information is actually really good for any kind of passive resistance for footings and all kinds of stuff. But one of the things he had to do that was calculate the passive resistance, the passive slip surface on this side as this pile cap gets pushed. And so he had to do earth pressures in doing that. And I don't know how this spreadsheet works. It's got Visual Basic, and I've been meaning for several years to go through and do my own little computational method for doing log spirals, and it's never happened. So I give you this instead. And if you're good at Visual Basic and you want to figure out how it works, that's great. And so 90% of this I don't use, or I haven't used for this purposes. But you can come in here and enter your friction angle. So let's say we got a friction angle of 35 degrees. You can input your wall friction angle if you want to enter it as a percent of the friction angle. So if you want it to be 30% of the friction angle, you can do that. Did I put a 3 or no? I didn't put a 3. That's 3 times backspace. 0.3 times this guy. You can do that, or you can just put in a value. It does it for cohesion too, so be sure to zero out the cohesion term if you want. Well, I'll leave a cohesion term in there for. And it'll calculate force and all kind of stuff. But one of the nice things it does is it calculates for you the Rankine active. You don't really need that one. The Rankine passive, the Coulomb passive, and the log spiral passive And the log spiral earth pressure is different if you got cohesion involved, so it's got one with cohesion and one without. But you can use these three numbers. This is how I developed that table, and compare the three right away. So that's a handy little way. This is only good for vertical faces and horizontal surfaces, so no one does those. But that's a lot of that'll cover a lot of cases for you, particularly for retaining walls, because lots of times when we're whoops, that's not the one I wanted. This is what I wanted. Particularly for retaining walls, because lots of times when we're using the passive earth pressure for retaining walls, what we're looking at is all we're really concerned about is what's going on down here, and we often have a horizontal ground surface in front of the wall, even if we've got a sloping angle behind the wall. And usually for most walls that aren't gravity walls, you have a vertical face here. So it's actually a pretty good solution for a lot of your passive pressures that you want to do. So if you want to calculate passive earth pressures and you don't want to go use the chart, there's a little tool for you. Now I promised we'd go back and cover part of what I rushed through last time, so let's do that. Because there's a really important thing that there's something I really blew through at the end that's really kind of important. Yeah, these two slides. Okay, so I want to cover layered systems, and then I want to point out one assumption in the earth pressure theories that is often overlooked and can mess you up. So the Rankine is strictly applicable only to homogeneous soils, as is the Coulomb. So normally what we do, we often have layered soils, and they got different strengths and different materials properties. So what we often do is just apply these theories layer by layer. And what I mean by that, if we have a soil with 3 different layers, what we're going to do is for the first layer, we'll calculate. Let's say we're calculating active earth pressures. We'll calculate Ka1, and for the second layer we'll calculate Ka2, and for the third layer we'll calculate Ka3, and then we'll just compute the vertical stress, and then we'll just compute vertical stresses as a function of depth, just like we would as gamma z. So we'll have a plot. If I was to plot sigma z as a function of depth, it might look something like this. Whoops, didn't do that very well. So we're going to have the sigma z, and then I'm just going to take my Ka's form, multiply by Ka, and I'll get an earth pressure diagram that looks something like that. Now that obviously can't happen. The earth pressure isn't going to suddenly have a step function there. It's going to look something like this. But that's normally what we do. It's a fairly simple simplification, and it seems to work okay. The whole point, one of the issues here is that if, for instance, this one applied, if this has a lower k than that it's a much stiffer soil. Well, you've got to make sure that you can actually you got to worry a little about strain compatibility here, because the stiffer soils will reach active pressures faster than the softer soils. The softer soils will take more displacement, so you have to worry a little bit about strain compatibility. So it could be, in some cases, that you got a strain compatibility problem. But that's pretty much what we do. Then I want to talk, I'm pretty sure, and I'll look on Blackboard real quickly, that I have a 1-page, might be 2-page summary that has all the earth pressure equations on it and all the notation on it. But the point I want to make, and it has all this information on it, the point I want to make is when there's a sloping ground surface, we always told you that K was equal to sigma h prime over sigma z prime, right? It's the ratio of the horizontal to vertical stress. Not really. That may be the philosophical definition of K, but mathematically, in both Coulomb and Rankine, K is the ratio of sigma A or P, whichever one it is, over sigma Z. In other words, it's the ratio of this total, it's the ratio of the resultant acting in this direction, not the horizontal. In the case of Rankine, it's beta. In the case of Rankine, it's the sloped at the back angle. In the case of Coulomb, it's at an angle of delta to the back face of the wall. So, and there's definitely some confusion about this. So when I use these earth pressure coefficients, notice that I'm calculating. These ones are stresses, and these stresses are in the direction. In the case for Rankine, they're parallel to the ground surface. In the case of Coulomb, they're in the angle delta to the back wall face. So it's not a horizontal. When you take sigma z times kp plus 2c times kp, you're not getting the horizontal stress. You're getting the Rankine stress or the Coulomb stress. And they're not necessarily horizontal. The Rankine stress is only horizontal when the back surface is horizontal, and the Coulomb stress is only horizontal if you assume delta is equal to 0, in which case it's the same as Rankine. Do you understand that that's really important? No. Go ahead.
Or is this that there's no closed form solution for sigma?
Well, let me see if I can, let me try again. So we always tell you that this is the, stop that. We always tell you that this is the equation for K, that it's the ratio of the horizontal to the vertical stress, right? And it's the first thing we tell you about horizontal earth pressure. It says, oh yeah, you take the vertical stress multiplied by K, you get the horizontal stress. Not necessarily having anything to do with walls or anything, right? That's just what we tell you the definition of K is. And so if you take K naught, you're out there and you're trying to do some solution, you know K naught, you take the vertical stress, you multiply by 1 minus sine phi to OCR to the sine phi, that's the horizontal stress, right? Does everybody agree with that? I need some feedback here also, I don't know what I'm doing. Okay, so when you're calculating, let's take the sloped angle because that's the better one. When you use this equation that PP is equal to, let me just use, when you use this equation right here, okay, for this problem, you're calculating the stress in this, oops, didn't do that very well. You're calculating the stress in this direction where this angle here is equal to beta and equal. You are not calculating the horizontal stress. That's the way the theory is set up. This is still Ka, the way we use it. I'm sorry, Kp or Ka. I did that one backwards. Let me be careful about that. I did the wrong equation. Did active here. If you want to know the horizontal stress, so this is the stress, and the force is just the integral of that, right? If you want to know the horizontal stress, then you've got to take PA cosine beta. This will equal the horizontal force acting on the wall, FH. And then the vertical one will be PA times sine beta. In both Rankine and Coulomb theory, the earth pressure coefficient is the ratio of the vertical stress to the resultant acting stress on the wall, not the horizontal stress. Does that make sense now?
So K active, would you just say that
It's really a coefficient for calculating Coulomb or Rankine earth pressure.
but there should be just a cosine beta attached to that, right?
Well, yeah, you can do that, but that's not the way it was defined originally. Yeah, I think it's better to. Professor Caduto and I had a long discussion about this in writing textbooks, and I think it's better to define it this way. And then I think it's better to define, because this is in this case the Rankine earth pressure. The Rankine earth pressure by definition is parallel to the back angle, and this is how you calculate it. So I think it's better to keep that definition with the Ka, and then say if you want the horizontal stress in a wall, you got to multiply cosine beta. The trouble with doing that is it sort of violates the original theoretical concept that K is a horizontal earth pressure coefficient, because it's not really a horizontal earth pressure coefficient. And I've seen people get around to say, well, this isn't the horizontal earth pressure coefficient, this is the Rankine earth pressure coefficient. The point is, if you don't understand this, you're going to be missing a cosine, and you're going to have the wrong answer. So I believe that in the literature, this is the best way to define it, and realize that what we're calculating is not the horizontal stress or the horizontal force necessarily. We're calculating the Rankine force, or in the case of Coulomb, I don't know if I have this here still or not. Oh, that's log spirals. That doesn't work. In the case of Coulomb, it's at an angle PA. Whoops. Right where this is delta. Is that clear? Because right, otherwise you're missing a cosine or a sine, and you'll have the wrong answer. It's easy to forget because lots of times we're working with horizontal surfaces, and all of a sudden you go to a sloped surface and you'll calculate it, and if you think that's a horizontal force, you're wrong. It's the force at the either angle delta to the back wall if you're using Coulomb, or at the back slope angle if you're using Rankine. Okay, I think that's all I wanted to cover today. I showed you the spreadsheet. Oh, I know what I was going to do. I was going to look to